The purpose of this unit is to go over the concept of enantiomers as well as define chiral carbons. By the end of this segment, you should have a clear understanding of what we're referring to when we talk about enantiomers. You should be able to identify two molecules that are related to one another as enantiomers. You should understand why we even care about whether two molecules are enantiomers to start with, and you should be able to recognize chiral carbons and how those relate to enantiomers. So let's go ahead and get started with this. First off, following up on our flowchart of the different relationships between molecules. When we talk about enantiomers, remember that enantiomers are the specific type of stereoisomer where the two molecules are related as non-superimposable mirror images, much like with your left and right hand. So we can take a look at the two structures right here, which are related as the so-called left-handed and right-handed versions of the molecule, or the enantiomers of this particular compound. In order for a molecule to have a non-superimposable mirror image, it has to have a chiral center. So a chiral center is a carbon that's bonded to four different groups. So I put a star on the carbon atom here. That's our chiral center, because that carbon is bonded to a carboxylic acid group. It's bonded to an amino group, that's our NH2 group. It's bonded to a hydrogen, and it's bonded to an R group. An R group is generally just a generic group that could be whatever we want to define it as there. So that's definitely a chiral carbon, and the structure on the right is its enantiomer, which also, of course, has to have a chiral carbon, a carbon with four different groups bonded to it. The reason we make a fuss about chiral carbons is that if a carbon is not chiral, in other words, if that carbon does not have four different groups bonded to it, then there can't be enantiomers possible. If a carbon is not chiral, what that means is that we would be able to rotate around another molecule to totally superimpose all of the atoms. So if we had a CH2 group, for instance, a CH2 group can never be a chiral carbon, and that particular carbon atom can't be the reason why two molecules are enantiomers. So if we had, for example, CH2, Cl2, that molecule is definitely what we refer to as an achiral carbon, meaning not chiral, meaning it does not have an enantiomer. And the reason is, if we look at it, there are no chiral centers in that molecule. There are no carbons that have four different groups bonded to it. So what that means is if we made the mirror image of this molecule, it would be identical to the structure that we started with. In order for the two mirror images to be non-identical, the molecule has to have a chiral center. So we could also think about like a carbon that's directly bonded to Cl, directly bonded to OH, directly bonded to CH3, and directly bonded to another CH3. This would also be an example of an achiral molecule. There's no chiral centers in that molecule, and therefore there can be no enantiomer. If we were to build this structure and to make a mirror image of it using a molecular model, we would find that we could totally superimpose the two molecular models by just rotating around carbon-carbon bonds or flipping the molecule over. And so therefore that molecule is achiral. In other words, it has no enantiomer possible here. There are a lot of really important molecules where the chirality, the concept of enantiomers, is really important. A few examples of those include ibuprofen. So ibuprofen, if we look at the structure, we should be able to pick out any chiral carbons that are present there. So looking through the molecule, this carbon atom here on the left, dotted with a red, is not a chiral carbon because that's two identical methyl groups bonded to it. The next carbon, not a chiral carbon because it has a CH2 group, so it has two identical groups, so can't be chiral. Coming on over to here, right here, I'm going to put a star on that carbon because that carbon is a chiral carbon. It has a methyl group, it has a carboxylic acid group, and it has that aromatic ring directly bonded to it, in addition to the hydrogen. And the hydrogen in line angle formulas isn't shown, but it's assumed that that has to be whatever fills in the empty missing part of the tetrahedron. So here, the tetrahedron is filled in with two lines, a wedge, and then the missing part would be the dash pointed away from you, which would be the hydrogen. You could put that either as a dash right there, on the left pointed toward the back, on the right pointed toward the back, whatever. What matters is that that hydrogen points away from you to fill in the tetrahedron. So when we're talking about a tetrahedron, we'll have to have two bonds that are in the same plane. So those are our two lines in this example I'm drawing. One bond that points toward us and one bond that points away from us to make a tetrahedron there. So this is going to be our tetrahedral carbon that I've put a box on, and that's your template for allowing us to show the orientation of the atoms here at an sp3 carbon in three-dimensional space. So the structure of ibuprofen that we've looked at on the left here is the mirror image of the structure that we're showing to the right there, which also has a chiral center, and we've shown that essentially there's a mirror right here separating those two structures. So they are mirror images of one another. And what's interesting about Advil or ibuprofen is that the structure on the left, that particular three-dimensional arrangement of atoms, is not going to be effective as a painkiller. On the other hand, the structure on the right is really effective as a painkiller. So it's the structure on the right that is marketed commercially to be used as the drug molecule. We could come up to the example up top here on the upper right. And on the upper right, this particular molecule, the star is already there on the chiral carbon. This carbon is chiral, and this carbon is chiral in this molecule because each of those carbons are bonded to 4 different groups. We have a nitrogen atom. We have a carbon that's bonded to an oxygen there, a CH2 group here, and then we have pointed away from us the hydrogen atom. So that's structure on the left certainly has a chiral carbon. The one on the right has a chiral carbon at the same spot there, and they are related as mirror images of one another. Thalidomide is a really interesting example because one of the enantiomers, the enantiomer on the left, is used as a treatment for morning sickness and a sleep aid, or it was back many, many years ago. On the other hand, the other enantiomer, the one on the right, is a teratogen, a substance that causes birth defects. And so what happened was when thalidomide was originally marketed, it was sold as a mixture of the two enantiomers. And obviously that led to some serious side effects. And as a result of those serious side effects of the molecule being a teratogen, thalidomide was pretty quickly pulled from the market, but unfortunately not in time for birth defects to be prevented. So there were some so-called children of thalidomide that were affected by this drug mishap, illustrating really how different enantiomers can have very, very different biological effects. The structure in the lower right is naproxen, which is more commonly known as the painkiller Aleve. We can pick out one chiral carbon in that molecule. That's the chiral carbon right here. And in that structure and its mirror image, so we imagine there's a mirror right here and we've drawn the mirror image of it. The structure on the left is an anti-inflammatory drug or painkiller. The one on the right is super toxic to the liver. So in the process of producing Aleve, these two enantiomers have to be separated from one another, and only the so-called S enantiomer is actually sold at market. You'll notice for each of these structures, we're using the terms R and S to denote the two different enantiomers of the molecule. And in the next segment, what we're going to do is go through how we go about assigning R and S, what terminology we can use and what we could pick out of the molecules to allow us to describe the three-dimensional shape of the molecule as the R chiral center or the S chiral center. So another question that may come to mind when we're talking about chirality is the concept of why are these molecules different in terms of their biological activity? Why is it that the R enantiomer and the S enantiomer of a particular molecule can have very different biological effects? The reason is that the different enantiomers, of course, have different three-dimensional shapes, and those three-dimensional shapes need to dock or match perfectly with the receptor that they're going to bind to. So the receptor is usually a protein target somewhere within the body, and the different enantiomers will match up with those or line up with those three-dimensional sites on the protein differently. So, for example, as an overview of this, we can take a look at the structure on the left here, and we see that the triangular group lines up perfectly with the complementary triangular site of the protein that it's lining up with. The square lines up with the square, circle lines up with the circle because the three-dimensional shape is correct. On the other hand, if we look at the enantiomer on the right, trying to line up and match with the same protein, we see that we have misalignment of circle with triangle, square lines up, but misalignment then over here of triangle with circle. And so therefore, that structure on the right can't properly bind into the receptor site, and therefore either there's very little biological effect or there's no biological effect. And what can sometimes be the case is that this second molecule that doesn't bind to the intended protein target can instead bind to a totally different target in the body, leading to some of those ill side effects that we don't desire for these molecules. So next what we're going to do is evaluate our ability to determine what carbon atoms within a molecule are chiral, because remember that this concept of finding chiral carbons is essential to recognizing whether or not a molecule will have an enantiomer. So we're going to identify the number of chiral centers in these molecules as our example problem. So example, mark the chiral centers with a star or with stars. So we'll go ahead and draw out some molecules here as our candidate chiral compounds. We're going to try to specify which carbon atoms within these molecules represent chiral carbons. So I'm just drawing out a few different structures here. As our possibilities. All right, so let's go ahead and start with these molecules where we're going to mark all of the chiral carbons in each compound using a star. So we're going to start with the compound in the upper left. And if you want to test your ability to do this, now would be a good time to hit the pause button, mark in what you think are all the chiral carbons, and then hit play to see if you are right or not. So starting with the compound in the upper left, remember that a chiral carbon by definition is a carbon atom with 4 different groups bonded to it. Now when we say 4 different groups, we don't mean that there's 4 different atoms attached directly. We mean entire groups that are bonded there are different. So let's take a look at our carbon atoms. We'll just go one by one and we'll mark off the ones with stars that are chiral. So this carbon here on the end, definitely not chiral. Anything that is a CH2 group or CH3 group absolutely cannot be chiral. So immediately you can add to your list CH3, CH2s, cannot be chiral carbons ever, because chiral by definition means 4 different groups, and a carbon can only have 4 groups in total. So here with CH3 and CH2 you definitely have some duplicating groups there. So CH3 is definitely a no-go. So I'm going to scratch off all of the CH3 groups from this molecule by just putting little dots on them to indicate we've cleared those. Those are not chiral carbons. CH2 groups, we can do the same thing. We can go in and go, all right, CH2 group is here and here. Those are definitely not chiral carbons. Then what we need to do is go in and look more closely at our remaining CH groups or quaternary carbons, carbons that have 4 bonds to other carbons. So these are our CH groups, and we have to ask at each of those, are there 4 different groups bonded or not, to identify which ones are chiral. So we're going to start with the one on the far left here. And does that have 4 different groups bonded to it? The answer is no, it does not, because the 2 methyl groups that are bonded here and here in blue are identical. Therefore, that carbon right here is not a chiral carbon. We come to the next carbon that was a candidate as a chiral carbon, this CH group, and we ask ourselves, does it have 4 different groups bonded to it? The answer here is also no, because this particular carbon has 2 isopropyl groups bonded to identical groups. So it has the isopropyl group here, and it also has the isopropyl group here. Those 2 isopropyl groups that I've highlighted in pink are identical. Therefore, that carbon that I put the blue dot on is definitely not a chiral carbon. So that's not chiral. Coming on to the next right here at this carbon that I've highlighted in pink, is that a chiral carbon? In other words, does it have 4 different groups bonded to it? Well, it has a methyl group. It has the alkyl group that is going off to the right there, which is different than the alkyl group it has going off to the left. It would also have a hydrogen atom bonded here to fill the octet. So therefore, this carbon does indeed have 4 different groups bonded to it. So I'm going to put a big star on that particular carbon to indicate that that is a chiral carbon. Coming onward to our next candidate for a chiral carbon, that's our next group here in yellow at the far right. That group has an ethyl group, a methyl group, the rather large alkyl group, and the unshown hydrogen there. That's 4 different groups, therefore that is a chiral carbon. So this particular molecule has 2 chiral carbons. If you're asked to specify how many chiral carbons are in this molecule, it would be 2. Coming on to the example problem at the top right, we go through the exercise again, first coming up with what our candidates are for chiral carbons. Those are definitely just carbons with 4 other carbons bonded, or the CH groups. They can't be CH3 or CH2 groups, so we have 1 here, and we have 1 possibility there. Everything else there is a CH3 or CH2, and therefore can't be possibly a chiral carbon. Now we need to go in and ask ourselves, do each of these carbons have 4 different groups bonded? So we look at the dot on bottom there in pink. It has an ethyl group, a methyl group, and the rest of the bulky carbon chain there, and the hydrogen, which we can put wherever we want in this particular structure. I'm just showing it explicitly to illustrate there are 4 bonds to that carbon, and that all of those 4 groups are different. So since those 4 groups are different, we'll go ahead and put a star on that carbon to indicate that it is a chiral carbon. Now we come up to that pink circle on top, which was our other candidate chiral carbon. That particular candidate is not a chiral carbon because it has 2 ethyl groups directly bonded. It has an ethyl group here and an ethyl group there. Therefore, it cannot be a chiral carbon. So this particular molecule has just 1 chiral carbon in it. Now we'll come to the lower left. And the lower left, we can immediately eliminate most of our atoms there because most of those atoms are part of CH2 groups. So the only atom left that we can't immediately eliminate is this one, the quaternary carbon right there. We call it quaternary because it has 4 bonds to other carbon atoms. But it has to have 4 different groups bonded to it. And here it has multiple identical groups bonded to it because if we go around the ring this way, like so, we're going to see that we run into the exact same things as if we go around in this other direction. The same will be true coming over here, same as coming this way to go around the ring. So therefore, this molecule has 0 chiral carbons. So in other words, this compound could not possibly occur in enantiomers. Any structure that you look at there has to be identical to any other structure that you look at. They can't be enantiomers of one another. So we come on over to our last example here, our lower right-hand corner example, looking for our chiral carbons. Carbons that have 4 different groups bonded to them. And I see a couple of candidates here for chiral carbons. Right there is a CH group. Right here is a CH group. And everything else going around the ring is a CH2 group or an alkene group. And remember that chiral carbons have to be carbons that are single bonded to other carbons. So looking at these 2 groups, starting with the carbon that's bonded to the hydroxy group, that carbon is directly bonded to a hydroxy group. It's directly bonded as well to a hydrogen, which I could put as a dash to the back left or back right. It doesn't matter which side you put that on. You just would need to recognize that it's there in the line angle formula. That's implied that that has to be the missing part of the tetrahedral shape. We've got a wedge, 2 lines, and therefore we have to have a dash as our missing part. So do we have 4 groups bonded to that carbon that's highlighted in pink there up top? And the answer is yes, we do. We have a hydroxy group, hydrogen. We have the carbon ring that goes off to the right, which is a CH2, carbon to the left, which is a CH. Definitely 4 different groups bonded there, so that gets a star. Coming over to this carbon atom, which I'm going to go ahead and put a star on as well, because it's directly bonded to a chlorine atom. It's directly bonded to the ring. Going up, we have a CH2 and then a carbon that's directly bonded to a hydroxy group, and that's definitely not identical to what you get if you go the same way around this direction. You come instead into an alkene group. So definitely different. They're not totally symmetrical going away from the candidate chiral carbon, and therefore we do have 4 different groups bonded here. So we'll go ahead and put that as a blue star as well as that other chiral carbon that we had marked already. And at this position, by the way, the hydrogen has to be pointed toward you, since that, in this case, would be the missing part of the tetrahedron. So this molecule we would describe as having 2 chiral carbons. All right, the next thing that we're going to do in this segment of getting familiar with enantiomers and this concept of chiral carbons is we are going to learn to draw the enantiomers of molecules. So we're going to do this by looking at an example where we're asked to draw the enantiomer of the molecule that I'm going to show you at left. And I'm going to trick this up a little bit by putting the S there with enantiomers, making this possibly plural. But remember that when I give you a structure, there's only going to be 1 compound that can possibly be the enantiomer of our starting structure. And so 1 at most, and don't let me fool you by putting that S in parentheses there. Okay, so we're going to start with this structure on our left, and we're going to draw the enantiomer of that. And there's two ways to draw the enantiomer. One is to imagine that you're creating the mirror image. Imagine that you're putting a mirror between the compound on the left and the one you're going to see on the right. The other way to draw an enantiomer is to leave the structure the same in terms of where the atoms are at on the page, except that you convert all the wedges to dashes and all the dashes to wedges. So you can either do the mirror image, or you can draw the molecule exactly the same as it was to start with, but convert all wedges to dashes and vice versa. So let's show those two different ways of going about drawing the enantiomer. And this strategy for drawing enantiomers here is a general strategy. It's not specific to this exact example. That's going to be what you'll do anytime you're trying to draw an enantiomer. So let's draw the enantiomer of this molecule. So we can draw the enantiomer of this molecule by imagining that we've installed a mirror. I'm just going to do dot, dot, dot to represent our mirror. And much like holding up your left hand and right hand, we can imagine if this molecule looked in the mirror, what it would see is what I'm drawing here. Okay, so we draw the mirror image of this, like so. So that's going to be one possible way to show the enantiomer. The other way to show it, rather than showing it by imagining that there's a mirror there, you can accomplish the exact same thing by drawing the structure exactly as we did in the upper left corner, right here, except that we take and convert all the wedges to dashes and all the dashes to wedges. That is also going to allow us to represent that we've made a mirror image. So I'm going to go ahead and draw in the structure the same in general as I did in the upper left, except that that wedge that we had to the hydroxy group becomes a dash to the hydroxy group. So this structure is another way of drawing an enantiomer of the structure that's boxed in the upper left in green. And so the two structures that I have drawn here, right here, are exactly the same molecule. It's just that we've rotated one around, we've flipped it over, going from one to the other. So these two structures circled in red are the same, and they are both enantiomers of the structure in the upper left. And so what we're showing here is that enantiomers always come in pairs, that the structure in the upper left is the enantiomer of, however you want to draw it, one of those two ways of drawing it in the lower right. Both of those structures are equally good representatives of enantiomers. So let's do one more example to make sure that we've got this down, this technique of drawing enantiomers. So we're going to go ahead and draw the enantiomer of this molecule. So we're going to go ahead and create our compound of interest here to start with. Just going to fill in this molecule. So in this case, we have two chiral carbons in the molecule, here and here. So to draw the enantiomer, we can do one of two things. We can either imagine that we've installed a mirror, like we did for the last molecule, and we can draw that object that would be seen in the mirror, or we can alternatively draw the structure the same as we did initially in the upper left, except that we take all the wedges and make them dashes and all the dashes and make them wedges. So our enantiomer here, if we envision that this object is looking into a mirror at itself, just like your left thumb and your right thumb are opposite, same thing here. And we'll go ahead and draw that out. So this would be the way of drawing the mirror image. The other way of drawing the enantiomer, and this structure that we're going to draw here is the same as the one up top, it's just a different way of representing it, is that we draw the two structures, that is the one from the upper left, the same, except that we convert all the wedges to dashes and all the dashes to wedges. So our wedge to a chlorine became a dash to the chlorine. The chlorine's still at the same spot. and our dash to the hydroxy group became a wedge to the hydroxy group. So that's going to give us this right here. So either of these two structures that I'm going to circle for you in red are perfectly acceptable ways to draw the enantiomer of the starting material. Let's do one last example here to make sure that we are on task with this. And in this question, we're going to say draw the enantiomer or enantiomers we'll go ahead and make our structure here, and we'll draw the enantiomer or enantiomers of it. So we're starting with this structure, asked to draw the enantiomers. You can hit pause to make sure that you actually know how to do this. And for this one, what you can do is imagine that you've installed a mirror. So we could draw the mirror image of our starting structure here. And the alternative to imagining that that structure is seeing itself in the mirror is that we could instead draw it the same as we did to start with, but convert all the wedges to dashes and vice versa. So you can convert the methyl wedge to a methyl dash, bromine wedge to a bromine dash. So either of these two structures that I'm highlighting in red are acceptable ways to draw the enantiomer of the structure on the left. So with that, we conclude our exercise in defining what enantiomers are, recognizing enantiomers, and identifying chiral carbons. In the next segment, what we're going to do is talk about how we can use terms R and S to identify the chirality of particular chiral centers. In other words, how to specify in words the three-dimensional shape of the molecule at a particular carbon atom. So stay tuned for that.